In the previous video, we looked at solving expressions for x, so rearranging, getting x by itself for expressions that involve exponential functions or exponential pieces. We'll look at some more challenging ones next, but we'll follow the same strategy. So on the left-hand side, we have 2 to a power is equal to 1 over 16 to a power. We need to make the bases match. What I'll do is I'll use 1 over 16 is equal to 1 over 2 to the power 4, which is 2 to the minus 4. So a two-step conversion process. First, recognizing that 16 can be written as 2 to a power, and then 1 over 2 to a power can be written as 2 to the negative of that power. So I'm going to substitute that in for 1 over 16. 2 to the 3 minus 7x is equal to 2 to the power of negative 4 times x. Then multiply using that rule of exponents. 2 to the 3 minus 7x is equal to 2 to the negative 4x. Now we can set the powers equal. 3 minus 7x is equal to minus 4x. I'm going to add 4x to both sides, subtract 3 from both sides. Well, I'll do that in 2 steps. So first add 4x to both sides, so we get minus 3x equals 0. Then I'm going to subtract 3 from both sides. I'll solve it a little bit of a different way than I did the previous ones. Then divide both sides by negative 3. And we get x is equal to 1. And you can verify that, go back and look up at the function, and you can verify that that's true. Okay, next one over. Don't be thrown off by the fact that there's a constant in front. We have an 8 multiplied by an exponential function. We're going to do the exact same thing. I need to make the bases match on both sides, including the 8 that's there. This will require another law of exponents. We'll use 4 is equal to 2 squared, and 8 is equal to 2 cubed. So we have to be a little bit more careful for this one. 2 to the 3x minus 2 is equal to 2 to the 3 times 2 to the power of 2 times x plus 1. So 2 to the 3x minus 2 is equal to 2 to the 3 times 2 to the 2x plus 2. Multiplying that 2 through the bracket using that law of exponents. Next step, we have to use a law of exponents we haven't used in these examples yet. We have a to the m times a to the n is a to the m plus n. So we're going to use that on the right hand side. 2 to the 3x minus 2 is equal to 2 to the 3 plus 2x plus 2. So 2 to the 3x minus 2 is equal to 2 to the 5 plus 2x. Now set the powers equal, since the bases are the same. It is extremely important that any constants you have in front are also brought into the base, if possible. If that wasn't an 8, if that was like a 6 or a 5, we'd be in big trouble. We wouldn't be able to use exactly this strategy. We'd have to use what's called a log function. All right, so now we set the powers equal. 3x minus 2 is equal to 5 plus 2x. I'm going to subtract 2x from both sides. X minus 2 is equal to 5. I'm going to add 2 to both sides. X is equal to 7. So that's our answer. You know, and that's really hard to check, because that says that 2 to the power of 21 minus 2, so 2 to the power of 19 is equal to 8 times 4 to the power of 8. And that's hard to verify. All right, next type. Solve for x. We have an issue with negative exponents, 9 to the x in the denominator, and we have a constant up above. So I'm going to rewrite this as 3 times 9 to the negative x is equal to 3 to the 2 minus x. So So that's just using exponent notation, bringing the positive power in the basement up as a negative power in the numerator. Now we'll convert the 9 into a base 3. We'll use the fact that 9 is equal to 3 squared. So 3 times 3 squared to the negative x is equal to 3 to the power of 2 minus x. I'm also going to do something a little bit sneaky. I'm going to call this 3 to the power of 1 times 3 to the 2x is equal to 3 to the 2 minus x. And now we're going to use the law of exponents to add those exponents together on the left. 3 to the 1 plus 2x is equal to 3 to the 2 minus x. Now we set the powers equal. Thus, 1 plus 2x is equal to 2 minus x. And we'll do some rearranging. So I'll add x to both sides. So 1 plus 3x is equal to 2, and then I'll subtract 1 from both sides. 3x is equal to 1, and then one more step to divide both sides by 3. Not a number that any of us would guess. The last one, the big challenge question, and it can be tested. It is testable. It is considered a hard question for this course and an easy gift question in Calculus 1000. And it's been given several times in Calculus 1000. So we want to solve for the value of x that makes this expression true. How on earth are we going to do this? We have 4 to the x, we have a base 4, minus 6 times 2 to the x minus 16 is equal to 0. We're looking for the x value or values that we can plug in and make this true. You can do it by guessing, but that's not very efficient. I mean, if it's a fraction, you'd be guessing forever. If it's a whole number, you're probably going to get it fairly quickly, but we don't know ahead of time what the answer is going to be. I'm going to show you a trick. I'm going to replace the 4 to the x with a 2 to the 2 to the x, since 4 is equal to 2 squared. Minus 6 times 2 to the x minus 16 is equal to 0. So this is 2 to the 2x minus 6 times 2 to the x minus 16 is equal to 0. And I'm going to do something really weird. Really strange. From this line to the next, I'm going to use the following law of exponents. I'm going to say that a to the m to the n is equal to a to the m times n, which is a rule that we've seen before, but now I'm going to write something you have not seen before. It's always been there. It's also a to the n to the m. The order of multiplication doesn't matter. N times m is m times n. So I'm going to use that to reorder the 2 to the 2x as 2 to the x all squared. So just look at the line that's one above that. Look at the second, look at the first line in purple. I just swapped the order of the x and the 2 inside the powers because they're both m times n. They're both 2 times x, the same as x times 2. Minus 6 times 2 to the x minus 16 is equal to 0. And now comes, if that part seemed magical, the next part's even more magical. I'm going to do what's called a substitution. I'm going to pick the letter t. I'm just making up a letter. You can use any letter that you want. I'm going to use t. Let t equal 2 to the x. And rewrite the problem in terms of t. Okay, so we have t squared minus 6 times t is equal to 16. Well, minus 16, not equal 16. Well, it is equal to 16, but I don't do that yet. Don't want to do any rearranging. All right, and this should look much more normal. This is a quadratic. We can factor it. We can solve this quadratic by factoring. We get t equals 0. We'll use the product and sum method. I want numbers that multiply together to give me 16, or negative 16, and add together to give me negative 6. And the answer would be negative 8 and positive 2. They add to give negative 6 and multiply to give negative 16. That means it looks like I have two solutions. First solution is that t equals 8. And the second solution is that t is equal to negative 2. Now there's two reasons why we're not done yet. One of the reasons is that it didn't ask us to solve for t, it asked us to solve for x. So I'll put that here. Need to solve for x. And the second reason we're not done yet will be apparent when we do this thing, the solving for x thing. So we'll use t equals 2 to the x. We'll undo the substitution. So this t is equal to 2 to the x, and this t is equal to 2 to the x. The one on the left is easy. 2 to the x is equal to 8, so 2 to the x is equal to 2 to the 3. That means x is equal to 3. The second one is a problem. This is impossible. Why is it impossible? Two to the x is always positive. Think about the picture of 2 to the power of x. I'll flip back to it. Oh, where is it? Right there. So the one in blue. This curve never dips below y equals 0, never becomes a negative y value. If you think about plugging numbers into an exponential function, like if you're evaluating 2 to the x, if you're plugging in any number like negative numbers, it just becomes 1 over the positive of that power. Positive numbers are just 2 to a positive power. You can't possibly get negative values out of that function. So the fact that it's saying 2 to the x is equal to negative 2, that's just plain impossible. We can't solve that, at least not with real numbers. So there's only one solution, only x equals 3. And I want to really emphasize that this is not a normal question. This is a challenge question. This is hard. Look at all the exponent laws we had to use to solve it. Okay, the last part of this part of the course is exponential functions that have a base that's special. So bases like 2 and 3 and 4, and even 1/2 and 1/3 and 1/4, they're not special bases. They're just either whole numbers or a rational base. There's a very special base for exponential functions. It's called the base of e. E is a number that has a value 2.71828, and the decimals go on forever. ... And you've seen one number like this previously. You've seen a number called pi. This should remind you of pi, where pi is equal to 3.14159, I think it's 9, 3.1415, I'm not sure if it's 9 or if it's 8, I'll just do ... Decimals go on forever. And there's not much that we can do by evaluating a function like this, like e to the power of 2. We have this weird decimal 2.71828 squared, and we can't do that by hand. So what we do in this section is we just review exponent laws and understand that there is this base e, there is this number e that plays a very important role in calculus. We're going to do more with that. But I should at least tell you where it comes from. I should at least tell you like okay, pi comes from circles, from circle geometry. Where does e come from? And that is a much more complicated question. One of the answers is that there is a geometric meaning behind e, but that's not where it came from. I will tell you where it came from. There's some more decimals of it. How much do we need to know? We need to know it's less than 3 and greater than 2. And if you want an approximation, you can replace it or approximate with 2.7. That'll be good enough for all applications that we look at. Some people really like E. When Google went public in 2004, that was a long time ago, their IPO, initial public offering, was $2.7 billion, and the rest of the digits matched the first few digits of pi, and they really wanted that. They were desperate for that because they're super geeks. So that should tell you something. They could have went for pi, 3.14, like 3.1 billion. They went below pi. They went for a lower valuation for their IPO just so they could have E. They lost money to pick E. I mean, they could have went higher. Everyone knows they could have went higher. But they wanted this so badly. That's how special this number is to them. Now, we don't care about that. Maybe, I mean, that's ancient history. That's one reason we don't care. Another reason we don't care is like, well, we can't do anything with that anymore. Even less connected to our current experience, but more important for appreciating like how math is done, like the process of discovering things in mathematics. That E was discovered by someone who was trying to understand compound interest. It was discovered by someone who was doing economics or finance. So this was a few hundred years ago in the 1600s. One of the Bernoulli brothers, there's several math geeks in this family, and econ geeks in this family, and physics geeks too in the family, full of geeks. This Dan guy was looking at compound interest. And what he was envisioning, he was doing like a mental experiment. He was envisioning a bank account that starts at $1 and pays 100% interest per year, compounded once, only at the end. And what would happen is that if you look at that interest rate formula, go back and plug the numbers in, after 1 year you end up with $2. You know, from $1 to $2 with a 100% interest rate. But what happens if you compound twice? What happens if you compound after 6 months and then after the 12-month mark, after the full year? Plug this stuff into the formula, and instead of getting $2, you get $2.25. And then what happens if you compound quarterly? So 4 times a year. You get $2.44. If you compound every month, $2.61. Compound every week, $2.69. Every day, $2.72. If you want to know the formula for compounding n times per year, there it is. It's just replacing the number. It's not replacing n, it's just leaving n as n. What happens if you let n go to infinity? You take a limit as n approaches infinity. And you can do this approximately, like you can put in n equals 1,000,000. So you compound 1,000,000 times a year instead of daily, which is 365. Or then do 1 billion, then 1 trillion, and then keep increasing the number of compounding periods. And what you find is that the number E comes out as the number of compounding periods goes to infinity. So E came out from explorations of compound interest. Now, it may have been discovered earlier than that, but this is what we have a written record of. So I'm going to have to go with that. But we know from all around the world, people were doing math for thousands of years. So for all we know, it could have been discovered thousands of years earlier and just never written down. When you look at a graph of e to the x compared to 2 to the x and 3 to the x, it doesn't look special. It's the one that's in blue. It's just sandwiched in between 2 to the x and 3 to the x because e is between 2 and 3. But the shape of it is the same. It doesn't look spectacular. It doesn't look like anything special is happening. So it's going to be kind of a wait and see type of a thing. Like, we're going to see why this E number is so special. We're going to see why we care about it in a calculus course and not just in an economics course or in an astronomy course, because it shows up there as well. All right, so that's the history lesson. Now, nuts and bolts. What's the homework look like for the section? It looks like this: using laws of exponents to simplify a number to a power. And the fact that this number, the base here in all cases is E, doesn't matter. If it was an A, or any general A, we would do exactly the same thing. So the first one, e to the 5 to the 4, is e to the 5 times 4, which is e to the 20. Second one, e to the 3 times e to the 7, is e to the 3 plus 7, which is e to the 10. Next one, that's a little bit harder to do. So I'm going to do e to the 5 over 2 minus negative 2, using that law of exponents. A to the m divided by a to the m is a to the m minus n. I have to be careful, I'm subtracting a negative, so this is going to turn into a positive. E to the 5 over 2 plus 2. Now we need to make common denominators, so e to the 5 over 2 plus 2 over 2, which is, not 2 over 2, 4 over 2, sorry about that. 4 over 2, which is e to the 9 over 2. And that'd be our answer. Okay, next one over. 1 over e. to the power of negative 3. Well, I can write 1 over e as e to the power of negative 1 to the power of negative 3. We have a power to the power is multiply, so e to the positive 3. Next one, we have e to a power, so that'll be the power is multiplying, e to the 5 over 2 times 6, which is e to the 30 divided by 2, which is e to the power of 15. That's our final answer. And the last one looks yucky, and it is a little bit yucky. We're going to have to do this in a few steps. I'm going to first deal with the first bracket. I have e to a power, so I'm going to multiply those powers. E to the negative 2/3 times 9. That's the e squared is still hanging out. So that'll be e to the negative 18 divided by 3. So e to the negative 6 times e to the 2, which is e to the negative 6 plus 2, which is e to the negative 4. And that's it. That'd be your answer. Okay, and I know we're past the 20-minute mark, but I want to motivate something. I want to motivate the next video, give you a reason to continue the story. I want to solve these next set of problems for x. 2 to the x is equal to 2. Well, that one's easy. X is 1. 2 to the x is equal to 4. That one's easy. X is 2. 2 to the x is equal to 8. That one's easy. X is 3. 2 to the x is equal to 64. We have to think about that one. So I'll put a 1, 2, 3, 4, 5, 6, 7. Maybe that's enough. So we multiply twice, we get 4. Multiply by 2 again, we get 8, so that's 2 to the power of 3. Multiply by 2 again, we get 16. Multiply by 2 again, we get 32. Multiply by 2 again, we get 64. So that's what we need. We need 64. So we need 6. X is 6. 2 to the power of 6, 2 times 2 times 2 times 2 times 2 times 2 is equal to 64. Okay, so that's all fine. How about this one? 2 to the x is equal to 5. So 2 to the 1 is equal to 2. 2 to the 2 is equal to 4. 2 to the 3 is equal to 8. So x is between 2 and 3. That's not very good. Just to say it's between 2 and 3. Like, is it 2.3? Maybe it's 2.4. Maybe it's 2.5. How are we going to find out? And the answer is that it's not possible to express the solution to this problem neatly as a fraction or as even a neat decimal. I'll just leave that. It's between 2 and 3. To do better than that, we need logs. A log function is the type of function that allows us to express the solution to this problem in an exact way. And we'll see that next time.